So let's talk about a few different types of numbers. Now, numbers have many different categories, but the most common one that people use are natural numbers, which are counting numbers, whole numbers, integers, rational numbers, irrational numbers, imaginary. To us, the most important ones are going to be real, irrational, rational, integers, and imaginary, because most of the time those are the numbers that we're going to use. Now, there's a few key differences between irrational and rational numbers. Okay? Irrational are number like square roots, cube roots, and special mathematical ratios like pi. They have the distinct property that they use infinite decimals. So, for example, 3.14519, etc., etc., etc. Those numbers will go on forever without repeating. Okay? So most of the time, things like the square root, the cube root of the same numbers, and numbers like pi and e are all irrational numbers. Now when I say irrational numbers, not all square roots are irrational numbers. Examples like that would be the square root of 4 and the cube root of 8. Both the cube root of 8 and the square root of 4 can be written as a fraction, okay, once you simplify it. For example, the square root of 4 is 2 and the cube root of 8 is 2 as well, which we can write as fractions. Rational numbers are all the numbers that you can write in a fraction. Those include numbers that have decimals but finish, like say for example 3.30, or repeating decimals like 3.33 repeated. Okay, those two numbers can be written as a fraction. They also include fractions like 1/3, okay, and perfect square and perfect cubes once you simplify them, of course. Technically, those are rational numbers. The idea is that if you can write it as a ratio of two whole numbers, okay, or two natural counting numbers, then it is a rational number. The third important category is imaginary. Okay, now imaginary numbers are things like the negative square root of 2 or the negative square root of 1. Generally speaking, they use square roots and fourth roots, although the roots could be higher, and we will talk about it in a later chapter. Okay, but those are numbers which specifically cannot be graphed in a Cartesian plane. We have to use a different coordinate plane to be able to graph them. And for our purposes, it also means that there is no solution. Things like 2i and 2 square root of negative 1 are also imaginary numbers. Anything with a multiple of square root of negative 1 as we simplify it will be an imaginary number. Now let's quickly write this list of numbers in the correct category. Now, what we're going to do is write it in the innermost category that you can think of. Okay, so for example, -1 is a real number. It's also a rational number, but above all else, we can think of it as an integer, okay? Because it's a whole number with a negative or positive value. In this case, -1. The next number that we have is 2.3. Now, 2.3 is a real number, and it's also a rational number. So we're going to write it over here. We do not write it in the category of integers because integers cannot be decimals, nor can they be fractions. So we have 2.3. 45 is the same thing as 1, an integer. 22 over 7 is a rational number because it's a fraction. Square root of -1 is an imaginary number, okay, because it's a negative number inside a square root, or an even root to be more specific. Then 1/3 is going to be a rational number. Square root of 3 is also imaginary. Once again, the idea is that you have a negative square root. So, that's there. 3.333 is a rational number because it finishes after the third decimal. If it is a finishing decimal or a repeating decimal, then it's a rational number. Otherwise, you could categorize it as an irrational number. 99 is an integer, so it's -10. Square root of 42 square root of 2 is an irrational number. And the reason why it's an irrational number is because the square root of 2 is irrational. So it automatically adds that element, okay, of being an irrational number. Now, the square root of 4 is an integer. And the reason being is because square root of 4 is equal to +2. Since it's equal to +2, and 2 is an integer, we write it as an integer. Square root of 12 is an irrational number, because if we were to simplify it, a concept that you're going to learn later on, you would notice that it's still an infinite decimal number. The negative square root of 12 is going to be imaginary because it has a negative on the square root. Pi is going to be irrational. It's one of those special numbers. I is by definition imaginary. 1,000,000 technically we can write it as a ratio or a fraction. Square root of 121 is an integer because we can actually simplify that square root. The cube root of 9 is going to be an irrational number, and you have to be careful about those cube roots because they're going to change the way we perceive things. In this case, it's an irrational number because the cube root, if you plug it into a calculator, of 9 would give you an infinite decimal. Same thing with the cube root of 81 is going to give you an infinite decimal. And the cube root of -81 is also an irrational number. The reason for that is because all these three can be simplified into something else. And the cube root of a negative number is still technically a real number. Okay, it's not imaginary as people think, because the imaginary numbers only apply for square roots and fourth roots and sixth roots. Okay, if you don't have one of those three roots that is negative, then you don't have an imaginary number. Which brings me to my last one. the square root of negative 4 is technically an imaginary number. Now what we need to go over is how to graph all types of numbers in a number line and eventually how to graph them in a Cartesian plane. Okay? This includes irrational numbers with square roots and fractions. Okay? Remember that imaginary numbers, you have to use a different number system in order to graph them. Now let's start with example 1, letter A. In letter A we have negative 1. That is pretty easy enough. Okay? It's just going to be this point right here. So we're going to put negative 1, and this is going to be A. Now, the next one we need to graph is 1.2. Now, this one has a decimal, so we need to figure out a way to correctly graph it. 1.2 is between 1 and 2, and it's closer to 1 because the decimal is closer to 1 than it is to 2. It's actually going to be 1/5 of the way between 1 and 2. It will be this point right here. Then we need to graph 3/2. Now 3/2 is equal to 1.5. So it's going to be smack in the middle of 1 and 2. Right there. And that's point C. Square root of 2 is going to be equal to around 1.4142, and it's an infinite number, so it can continue going on to forever. But for right now, we're going to use 1.4, okay, as our closest estimate, and it's going to be in between point B and C at 1.4, and that's going to be the square root of 2. Now, remember that the square root of 2, you are using an estimate to actually graph it, okay, so you're going to try to get it as close as possible. Of course, it's not going to be somewhere in 6 or somewhere in the negative line. It's going to be between 1 and 2, and specifically between 1 and 1.5, closer to the 1.5. Then the last one is 3 square root of 3, and like before, the best way to do it is to plug it into the calculator to get an estimate, and that is going to be equal to 5.919615, etc., etc., etc. Okay, so we're going to round it off to 5.2, which is somewhere down here. Okay. And that's pretty much how you graph points in a number line. Whenever we're dealing with irrational numbers and rational numbers specifically, you're always estimating. Some estimates are going to be more accurate than others. 1.5 you should be able to find relatively easy. 1.2 is going to give you a difficult more time. So we're going to quickly go over how to graph the Cartesian plane. Okay, you're usually going to be given two coordinates, an x, which is always the first number, and a y, which is always the second. And generally speaking, you can think of the x-axis and the x and the y-axis as two coinciding number lines. And like the number lines, if you need a decimal or an irrational numbers, you're going to go in between the numbers. So the first one's easy. You have -1, 2, which brings our point right here, point A. When we need to find B, we go between 1 and 2 for 1.5, and between 1 and 2 for y as well. Okay, and that's going to be our point B. For point C, Same principle, only different type of decimal. You're going to go in the x-axis between 1 and 2, but you will be somewhat closer to 1, a lot closer to 1 than you are to 2, 1/5 of the way precisely, okay? And you're going to go to negative 2.4, which is somewhere around here, 2/5 of the way down. And that's going to be C. Okay, notice that I went down because we had a negative number. Okay, those directions still technically apply. For negative square root of, negative 3 over 2, okay, you're going to get a decimal. So negative 3 over 2 is equal to negative 1.5. And 7 over 3 is going to be equal to about 2.3 repeating. Okay, so the negative 1.5 is right here. That's the x. And then 2.33333, despite the fact that it's a repeating number, is one of the a third in between, 1/3 in between 2 and 3. So it's going to be somewhere around there. And that's going to be D. The last one, we need to figure out the approximation for the square root of 3. Now the square root of 3 is equal to 1.73, and then it continues on forever. So we're going to approximate to 1.7. Okay, that's the closest approximation that we can have. And it's negative. And the other one's going to be 4. So we're going to go to negative 1.7, which is a little bit above here. Okay. And we're going to go to positive 4, which is all the way up here. And that's going to be E. Notice that a lot of this we eyeballed, okay, what 1.5 would be, okay? The idea is that when you graph something, especially when you're dealing with decimals, okay, it's not always going to be as accurate as it would be if a computer was doing it. And I will take that into account. Now it needs to make sense, okay? You cannot have 1.5 be somewhere right here, okay? But our purposes is still technically the same. We're trying to, as best as we can, with the tools that we have, to graph the points. And that's what you're going to do on the homework. Now we're going to begin factoring, okay? And factoring depends on knowing prime numbers. So for right now, I want you guys to remember this list of prime numbers. 2, 3, 5, 7, 11, 13, 17, 19, and 23. Okay? Most of the times we're going to be in this range right here, but it's not uncommon to go into that range. Now, 2, 3, and 7 are all going to be prime numbers. We wrote it on the list right here. But this is the reason why. When you divide 2 by itself, you get 1. And those are the only two factors, possible factors you're going to have. Therefore, they're prime. Next, when we try to do exactly the same 3 with 3, you're only going to have 2 factors as well, which means that this is also prime. Now the difference between a prime and a composite number is the number of factors. For 4, when we do so, you notice that we start with 2, we divide, 4 divided by 2 is 2, divided by getting by 2, you get 1. Now we have 1, 2, and 3 factors, which makes this a composite number. 7, like we talked about before, can only be divided by 7 and 1, so it's prime. 12, okay? Now, as number starts getting bigger, you have to actually follow a specific process. You're going to always divide by the smallest prime number you know, which in this case is 2, okay? And you continue dividing until you cannot divide no longer by 2. Then you're going to try dividing by the next prime number, and when you're done dividing by the next prime number, you continue with the one after that. So 12 divided by 2 is 6. Then you're going to divide it by 2 again, which gives you 3. Now 3 cannot be divided by 2, so we have to go to the next list of numbers, which is 3. When we divide 3 by 3, you get 1. So this is also a composite number because obviously it has more numbers. And its factors are 1, 2, 2, and 3. And it has a total of 4. Now that's making that list is going to be important later on. 42 is the same principle. 42 divided by 2 is 21. 21 cannot be divisible by 2, but it is divisible by 3. So 21 divided by 3 is 7. And then 7 is not divisible by 3, it's not divisible by 5, nor is it divisible by 3. So the next number on the list would be 7. And when we do so, those are the numbers you get. So it's also composite. And the list is going to be 1 times 2 times 3 times 7. Now 23, okay, cannot be divided by 2, cannot be divided by 3, cannot be divided by 5, cannot be divided by 7, cannot be divided by 11, cannot be divided by 13, cannot be divided by 17, cannot be divided by 19, and cannot be divided by, but it can be divided by 23, which is simply itself. When we do so, we get 23 and 1, which makes 23 one of the bigger prime numbers. 72. 72, since it ends with a 2, therefore an even number, can be divided by 2. 7 divided by 2 is 3 times, carry the 1. 12 divided by 2 is 6 times, so you get 36. 36 can still be divided by 2, you get 18. 18 can still be divided by 2, you get 9. 9 cannot be divided by 2, but it can be divided by 3, so you get 3. And 3 divided by 3 is 1. So the list of factors are going to be 1 times 2 times 2 times 2 times 3 times 3. Now that list is going to become longer and it's going to become much more important once we start doing radicals and once we do fractions. So keep that in mind. Even if the process is long, okay, you need to be able to do this. Now, obviously, by this point, you can kind of see the pattern. 27 cannot be divided by 2, but it can be divided by 3. So the factors are 1 times 3 times 3. I made a mistake there. There we go. And 47 is also a prime number, like 23 is one of the bigger ones. So it can only be divided by itself and 1. So the answer would be 1 times 47. Now in example 2, we need to make a possible list of factor pairs for each of the numbers. So that means that now we're going to have a list of factors, okay? But we can only have 2 at a time. I'll give you an example. 1 times 2 is a factor pair, because if we multiply 1 times 2 together, you get automatically 2. Same thing for B. 1 times 3 is only the only factor pair. Now things start getting a little bit more difficult as the number becomes composite and the composite number becomes bigger. So in the case for for letter C, one factor pair is the number times itself and 1, and the other possible number is 2 times 2, both of which still give you 4. We go back the prime number, which is only 1 times 7, and the composite number 12 has different factor pairs, okay? The list goes like this: 1 and 12, 2 and 6, 3 and 4. Now, an easy way to remember this, you always start with the smallest number, with 1, and work your way down to 2, 3, and 4. As your numbers get closer, you know you're going to get to the end of the list. We're going to follow this process with 42. With 42, we start with 1 times 4. Then since 42 is divisible by 2, we're going to start with 2 times 21. Notice that both of the numbers are getting closer and closer to each other. Then we're going to continue with 3 times 14. It looks like we're going to have to do 4. Actually, I don't think 4 works in this case. Okay, so we're gonna, 5 doesn't work, but 6 does. And you're gonna get 6 times 7. So that's the list of the possible factor pairs. For 23, since it's a prime number, the only factor pair that works in the case is 1 and 23. 72. Now, the bigger the number, the longer the list, especially if it's a composite number. But 72, the first one is going to be, obviously, 1 times 72. Then we're going to continue on with 2, which gives me 36. Now, we can do it by 3. So, the first number is 3. And the second number is going to be 24. We could also do it by 4, which brings the next number to be 18. 5 doesn't work. 6 will work. Brings you 12. 7 doesn't work, but 8 does. 8 times 9 is going to give you 72. Now notice the kind of the simplicity of this. 1, 2, 3, 4, skip 5, 6, skip 7, 8. Okay? As the numbers get really close, that if you kept going, you start going back the list, you can stop. So those are the list of possible factor pairs. And we're going to use them when we are trying to factor quadratic trinomials. The next one is going to be 1 and 27. 2 doesn't work, but 3 does, and you get 3 and 9. Okay? And then the next one would have been 9, so we can actually stop right there. Those are the two possible factor pairs. And for the last one, since it's a prime number, it's only 1 times 47. So remember this process because we're going to need it in quadratic trinomials. Now the homework is right below, so you can go ahead and finish that. Okay? I want you guys for homework to find the first 20 prime counting numbers. Okay, you can look them up online or you can actually get them by hand. The rest is exactly the same as the examples. We're now going to add fractions. In order to add fractions, we need to always have the same denominator. Okay, so all denominators need to look the same. If they don't, we need to change it. So let's make a note of that. need the same denominator. Now for the first one, we already have the same denominator, so all we need to do is rewrite it a single denominator, and we're going to add the top. 1, 7, and 17 added together. If you add those three things together, you get 25 over 5. Simplify, you get 5 once you divide 25 by 5. Now in example 2, we have fractions with different denominators. Our first step is going to be to figure out how different they are and to make them the same. In order to do so, the first thing that you're going to do is to rewrite them with the composite denominators broken apart. For us, that means that, for example, 10, which is the composite number, right there, is going to be broken apart into 2 times 5, and 15, which is also a composite number, is also going to be broken apart into 3 times 5. Now notice they're different, and keep that in mind. Once we break them apart, we're going to multiply each fraction by its missing factor. So for example, the first fraction is missing a 2 because the second fraction has a 2, and it's missing a 3 because the third fraction has a 3. Then the second fraction is still missing a 3 from the third fraction, so we need to multiply by 3. And the last fraction is missing a 2 from the second fraction. Okay, what you'll notice is that we should have the same numbers in the denominator. Okay, we have 5 on all 3 of them, 2 on all 3 of them, and 3 on all 3 of them. That means that we have the same denominator, even if they're not organized the same way. Once we multiply them together, you should get back your original denominator. Okay, so we're going to write 2 times 3 times 5. Now, on the top, we're going to write the numbers simplified. 1 times 2 times 3, which is the first one over here. Okay, is going to be 6. Then 21. Then 18. Now, I'm going to hold off in simplifying the bottom, because what we need to do is see what number we get. When we add all of these together, you're going to get 35 or 45. Let me double check my math. 6 plus 21 is 27. 27 plus 18 is 45. Okay, so we're going to get 45. Now the reason why I didn't put it all the way over here with my fraction is because I also want to break apart 45 and see if we can actually cancel out some numbers. Okay, so 45 can be broken apart into, let's do it over here. It's not divisible by 2, it is divisible by 3, and it is divisible by 5. So it can be broken apart into 1 times 3 times 3 times 5. On the bottom, we still have 2 times 3 times 5. I purposely did this because what we're going to do next is we're going to cancel out anything that repeats. 3 on the top, 3 on the bottom cancels out. 5 on the top, 5 on the bottom cancels out. The only thing left is this 1 times 3 on the top over 2. Simplify that, you get 3 over 2. Now notice the advantage. We factored, okay? That is very important when we're dealing with fractions. If you're not able to do this, you're not able to simplify very efficiently, especially bigger numbers. Now for the second one, in order to add example 3, what we need to do is figure out what least common denominator is. So we're going to first write all the fractions, and if we have a composite number in the denominator, we're going to break it apart into its factors, so we know what factors each denominator is missing. Now if you look at this problem, you'll notice 5 is missing 7, 2, and 3. 2 is missing 7 from one, and it's missing 2 and 3 from the other. And when we always have to multiply the top and the bottom. Then 7 is missing 5, 2, and 3. Lastly, 11 over 6, which is 2 times 3, is missing 7 and 5, both on the top and the bottom. Once we know what numbers we need to multiply, both the top and the bottom, we have to go back and make a single fraction, add the numerators together, once we simplify it, of course. Okay, on the bottom we're going to have 2 times 3 times 5 times 7. I'm going to leave it in its factor form, in its prime factor form, in case we need to cancel out later on. Now, on the next one we have 7 times 1 is 7, times 2 is 14, times 3 is 42. On the second one we have 25, 5 times 5 is 25, times 2, 50, times 3, 150. Then we have 11 times 7 times 5, which gives you 385. Now we're going to add all three together. And you're going to get 577 over 2 times 3 times 5 times 7. Notice that I haven't simplified this. Okay, I'm going to see whether or not I have something that I can divide by, so we can simplify. Now, since we have the prime factors, and they so happens to be the first 4 prime factors that we would use in order to figure out, I'm going to see whether 577 can be divisible by 2, by 3, 5, or 7. 3 is the first one, it doesn't work. We know it's not divisible by 5 because it doesn't end in 5 or 0. And it's not divisible by 7. So it turns out that this is the simplest form secant half. So we just need to put the numbers together. So we have 6 times 5 is 30 times 7 is 210. That's your final answer. In example 4, we need to do exactly the same thing as example 3. We first need to rewrite the expression, okay, making sure that we factor any composite numbers. In this case, the one composite number that we do have is 21, which we have to factor into 3 times 7. Now, we have to multiply both the top and the bottom by numbers from the other denominators that the first, second, and third fraction are missing. What I mean by that is, let's say, for example, 1 over 7. 1 over 7 is missing 23 from the second fraction, and it's missing 3 from the third. So we need to multiply by 23 the denominator of the second fraction, and 3 part of the denominator of the third fraction. And of course, 23, we need to multiply both by 3 and 7. And 11, we need to multiply by 23, which is the denominator of the second fraction. Now, the denominator for all three of them added together is going to be the same. Okay, they have to be the same because we eventually take it away and just use one of them. So we have 3 times 7 times 23. And then we have to simplify each one of the fractions. 23 times 1 is 3. 23 times 3 is 69. Then we have 3 times 17 times 7, which will give you plus 357. Now, a common mistake that people make is to forget this negative right here. So we have negative 11 times 23, which is 253. Once we have all of this, we need to perform the operation. We're going to add 69 and 357 together and subtract 253. And the answer that we get is 173 over 3, 7, 23. Now, since the bottom is already a set of prime numbers, we can simplify this if 173 is divisible by any of those three numbers. As it turns out, it doesn't look like it's divisible by any of the three numbers. So that is its simplest form. We just have to change the denominator into a single number. Which is 483. Now the last fact that we need to complete is multiplying and dividing fractions. Okay, to multiply fractions, you have to remember that you have to multiply within its level. Okay, that means the numerators are multiplied together and the denominators are multiplied together. If you have a case in which you have a whole number with fractions, you're always going to assume that the whole number has a denominator of 1, okay, as is in example A, or example 5, problem A. Okay, you're going to notice that we have a whole number, 7, multiplied times 1 over 14 times 5 over 19. Okay, so we're going to multiply everything together. 7 times 1 is 7, times 5 is 35. And on the bottom, we are going to get 1 times 14 is 14, times 9 is 126. Okay, now this one can be simplified because both of them can be divisible by 7. You're going to get 5 on the top and 18 on the bottom. Now, in case we have 3 fractions, okay, we have to do the same thing. Okay, you're going to multiply the top and the bottom to each other of all 3 fractions. Now, there is a faster way to simplify it, specifically when you also have kind of the factors. If you notice that something repeats both in the top and the bottom, they automatically cancel each other out. Okay, in this case, 3 and 3 cancel each other out because 3 over 3 is equal to 1. So you now have 1 times 8, which is 8, and 14 times 14, 7 times 7, which gives you 14. Actually, my bad, gives you 49. And that's your final answer. Now, division of two fractions, or division between a fraction and a whole number, takes a different meaning. Okay? Because we have a division, we always have to remember that division is the opposite of multiplication. Okay? Where multiplication makes something bigger, division cuts in size. In order to account for that, okay, we normally change, when we're doing fractions, we normally change division to multiplication this way. The best way to remember how to do it is to remember this acronym. KSF, which stands for keep it, switch it, flip it. Okay, we're going to keep the first fraction. We're going to switch the sign, the operation, and we're going to flip the second fraction. So let's look at example 6, letter A. We have 1 over 6 divided by 3. If we follow keep it, switch it, flip it, we have to keep the 1 over 6. We have to change the division sign to a multiplication. And we have to change the second fraction. Now, that means that for us, we have to change 3 into 1 over 3. Remember that every whole number is still a fraction with that denominator of 1. Okay, we just assume that everybody knows that. Okay, and we don't use it. Once we have that, all we need to do is multiply the top to the top, bottom to bottom. So you have 1 over 18. That's your final answer. Now, let's continue on to example B. Now, example B has two straightforward fractions. You're going to have 7 over 3, which you're going to keep. You're going to change the division sign to a multiplication. You switch it, and then you're going to flip the second fraction. It now becomes 7 over 1. Then we multiply the top to the top, bottom to bottom. You're going to get 49 over 3. That's your final answer. A few things you should notice is that multiplication and division is a lot easier than addition and subtraction. Okay? So you should not have any trouble with it. Okay? Just remember that for division, okay, you have to keep it, switch it, flip it. So now we're gonna be simplifying and adding radicals. Okay? In order to simplify radicals, the best way to do so is to identify what radical we have, okay, and trying to simplify it by factoring out the number into its prime factors. Now, some radicals are going to be easier than others. Let's say, for example, A. We have the square root of 36, which is obviously 6. Other ones you actually need to try out. In this case, we have the square root of 18. Now, what we can do is split apart the square root of 18 into its prime factors. We start with 2, you get 9. Then, 9 is not divisible by 2, but it is divisible by 3. You get 3. 3, 1. What we need is the prime factors, which in this case is a list of 2, 3, and 3. Okay? For every 2 numbers that repeats, 1 gets to go out. So in this case, there are no repeating 2s, so the 2 has to stay inside the radical. They are, however, repeating 3s, which means that the 3, one of them gets out while the other disappears. Okay? So the correct answer would be 3, which we got to put outside the radical, square root of 2, which had to stay. Now, radicals could be a big or small, okay, and they can have numbers in front of the radical. If the numbers in front of the radical treat it as normal multiplication, you're going to simplify the radical first, and then you're going to multiply it to the number that's outside. In this case, what we're going to do is we're going to try to simplify the square root of 48 first, and afterwards, we are going to multiply it by 5. So, in order to simplify the 48, we need to factor 48 into its prime factors. Okay, so 48 is divisible by 2. And we end with a factor of 3. Now you notice that you have multiple 2's, okay? So you have to take 2 at a time. First, if you have, for every 2 2's, you take 1 out. So this one is gone, the second one goes out. This one is gone, the second one goes out. So outside, you're going to have a 2 and a 2. And of course, the 3 doesn't have a pair, so it has to stay inside the radical. So if we were to simplify this, you would get 2 times 2, which would be 4 square root of 3. Now going back to the expression we had earlier, we had 5 on the outside times 4 times the square root of 3. We need to distribute the 5 into the 4, and you would get 20 square root of 3 as your final answer. Now, square roots are not the only roots that we have. Sometimes we have higher power or higher order roots, which we call cube roots and fourth roots. Now, a cube root simply means that we're looking for 3 numbers that multiply together give you that number, okay? And the process is very similar, okay? First off, remember that the number in front is simply multiplying to the radical, so we're going to put it outside the parentheses with the radical inside. And we have to simplify the radical inside first before we can multiply it to the 8. In order to simplify it, we have to split apart the 96 into its prime factors. Now this list is going to be longer because 96 is generally what we consider a big number. So divide by 2, you get 4 and 8, then you get 24, then you get 12, then you get 6, and then you get 3. Now, the difference between this cube root and the other square roots is the fact that we have an index of 3. So instead of taking out every second repeating number, we're going to take out every third repeating number. That means that we take out 2, we take out 2, the third one goes out. So this 2 has to go out. Now, because we don't have another set of 3 2's, okay, nothing else can come out. So that means the 2 squared and the 3 have to stay inside the radical. So simplified, the cube root of 96 is going to be 2 on the outside. Cube root of 2 times 2 is 4 times 3 is 12. Okay, remember that was inside parentheses, and we still need to multiply by 8. So 8 times 2 is going to give you 16. So the simplified form is 16 square root of 12. Now remember that simplifying radicals is very important, because later on when we add them, we need to be able to simplify them. As a general rule, if you want to add or subtract radicals, you always need to remember that you need to have the same radical. In fact, it works very similar to when you have fractions. The limitation of this is that if you have different radicals, you won't be able to add them together. Okay? So, different radicals you won't be able to add together unless you can simplify them, and after you simplify them, you get the same radical. Now, in the first one, okay, you'll notice that we have the same radical, which is the square root of 3. Okay? Since we have the same radical, all we need to do is add the coefficients, the number in front of the radicals, which in this case is 10, -4, and -7. So we're going to have 10 minus 4 minus 7, okay, square root of 3. Add them together. 10 minus 4 is 6, minus 7 is -1, square root of 3, or negative square root of 3 is fine. Okay, just remember that we need to have the same radical. If we don't, if they differ in any way, we cannot add them together. So in this one, in the next one, okay, you'll notice that this and this is the same radical, but this one is not. Okay, so 11 square root of 3 we won't be able to add. The only ones we will be able to add is the square root of 2 and 13. Now remember that even if you don't see it, there's always a 1 next to the radical, next to a variable, next to a number. So you're going to have 1 from this one minus 13 square root of 2 plus 11 square root of 3. You're going to get -12 square root of 2 plus 11 square root of 3 as your final answer. Now it's a little bit better, okay, but that's as much as we can simplify for the moment. Now, radicals can not only differ on what's inside, but also on the index itself. Now remember, the index is the little number on the top. Now in this one right here, you have to be cautious and always look to all parts of the radical. You'll notice that this has an index of 3 and this has no index, which implies that the index is 2. And this has an index of 3. Okay, so it would assume that you could not add anything. However, before you can assume that, always make sure you simplify the radicals, okay, as much as you can. So obviously we cannot simplify the cube root of 2 and the square root of 2, but we can simplify the cube root of 16. What we need to do in that case is to write its prime factors. 2 you write your prime factors, remember that we have to always look at the index. We need 3 numbers in order to take 1 out. So 1, 2, the third one goes out. This one doesn't have any more numbers under it. Okay, we don't have the other 2, so it could get out. So this one has to stay inside the box. Okay, so simplified. The cube root of 16 is 2 cube root of 2. Now you'll notice that we do have another cube root of 2. Okay, the first number and the front, which means the first and last terms can be added together. You're going to have 3 and 2 cube root of 2 minus 7 cube root squared. The final answer is 5 cube root of 2 minus 7 square root of 2. Okay? Now these two, even though they have the same number inside, cannot be added together because the index is different. So different index and different radicand, which is the number inside, means that you cannot add them together. Now the last one that we're going to work on is D. Now you'll notice that D has different radicals, but 2 of the radicals can be simplified, which is this one, the square root of 72, and the square root of 8. So like before, we're going to find its prime factors. Okay, we have 2. Let me use a different color. So 72 divided by 2, you get 3 and 6 divided by 2 again, you get 18. By 2 again, you get 9. We start with 3, and those are the numbers you get. Now in this case, for every 2, because we're using square roots, for every 2 that we have, 1 goes out of the radical. So this first one disappears, the second one goes out. Now there is no other 2 that we can use to take it out, so this one has to stay inside the radical. 3 dies, and the other 3 gets to go out. So the simplified version is going to be 2 times 3 square root of 2. So we're going to get 6 square root of 2 as a simplified version of the square root of 72. Now 2 square root of 2 we cannot simplify, so we have to leave it alone. But we can simplify the square root of 8. You're going to have 8, which is this number right here, and we're going to start divided by 2. Like before, you have to remember that for every 2, only 1 goes out. So this one's gone, the second one gets to go out, and this one doesn't have a little twin that it can use to go out, so it has to stay inside the radical. Okay, so 8 times 2 square root of 2. The 2 from here, and the other 2 here. Let's go ahead and simplify this so we can add them together. You have 6 square root of 2, that's already simplified, minus 2 square root of 2, plus 16 square root of 2, because we have to recombine 2 and 8 together. Now, remember that we're only adding the coefficients. So we're going to have 6 minus 2 plus 16 square root of 2. 6 minus 2 is 4, plus 16 is 20. So the correct answer is 20 square root of 2. Now, last thing that we need to do is dividing and multiplying radicals. Now, dividing and multiplying radicals requires you to be very, very, very good at factoring and remultiply numbers together. Now we're going to start with A. Now in A, you have to remember, okay, that you're going to multiply everything on the outside together and everything on the inside together. The same principle that we followed when we did fractions. We multiply top to top, bottom to bottom. So if you want to think about it, on radicals, you have to multiply outside to the outside, inside to inside. So in this case, we will have 2 times 12 and square root of 12 times 12. You will have 24 square root of 144, and the square root of 144 is a perfect square root, which gives you 12. So 12 times 24 is going to give you 288, I do believe. Yep, the answer is going to be 288. Same thing for the second one. Multiply the outside to the outside. You get 44, right? 4 times 11. And then you're going to get 3 times 12, which is the square root of 36. We know 36 to be a perfect square root, okay? Which becomes 6. Now we have 44 times 6, which is 264. Now, there is a little caveat, okay? Normally speaking, whenever we have a different index, and you'll notice this in example C, we won't be able to do it by this method alone, okay? Because it simply will not work, okay? Normally, what we need to do is convert the radicals into rational exponents. Rational exponent is simply a radical that has a fraction for an exponent, okay? We're going to try to do that and see if you can follow along, okay? But we will cover this in another section as well. So, for right now, remember, outside to outside gives you 44. Now, the way that we're going to try to deal with this is that we're going to multiply. We're going to change the square root of 3. Now, this is what happens. The square root of 3 always has an index of 2. We just never write it. Which means for us, okay, if we wanted to write a fraction on the exponent, we would have to write it like this. 3 to the power 1/2. Now, here's how I got 1/2. The denominator of the fraction is the index. The numerator is the power of 3, which in this case, since we only have 1, it's going to be 1. So we're going to have 3 to the 1 over 2. And then for the other one, since we have an index of 3, we're going to have 3 to the 1/3. Now, there's something called the power rule, okay, that says whenever you multiply two numbers with the same base, in this case the base is 3, you're going to add the exponents. That means that we're going to have 44, 3, 1/2 plus 1/3. Of course, since it's fractions, we need to actually have a common denominator, okay, when we're adding the fractions together. And you're going to have 3 over 6 plus 2 over 6. And you're going to get 3 to the power 5 over 6. Now we technically have combined the two radicals together. Now the correct answer has to be in radicals. Okay, so we have to convert it back. We're going to have 44, and then you're going to have the 6th root. Notice how the root is bigger of 3 to the power of 5. Okay, and that's your final answer. That's how you combine radicals. For right now, however, you can assume that you cannot combine them if the index is different. Okay, if the index is the same, you should be okay. So let's go ahead and try the next one. Alright, so for the next one. Okay, notice that we won't be able to immediately do 10 cubed root of 3 because we would have to use the method from before. So we're going to avoid that and just multiply the 8 square root of 12 and the 3 square root of 3. Okay, so you're going to have 8, okay, times 3, which gives you 24. Now, the numbers on the outside, you're more than welcome to multiply together. That means that we're also going to multiply it to the 10. 24 multiplied times 10 gives you 240 instead of just 24 alone. But now, we're going to have the square root of 3 times 12 times the cube root of 3. Now, when we simplify this, you'll notice something interesting. 3 times 12 is 36 times the cube root of 3. Now, the square root of 36 is a perfect square root, and you're going to get 6. Now we have 240 times 6 times the cube root of 3, which will give us 1,440 times the cube root of 3 as our final answer. Now, when dividing radicals, okay, what people will tell you, or what people do not tell you, is that you technically cannot divide radicals because of its powers, okay? What we're trying to do instead is to avoid having a radical in the denominator, okay? Which is actually very easy to do. Okay? So let's look at example 4, letter A. You'll notice that the only radical in the denominator in this case is the square root of 12. Now, there is a way to multiply by another square root, okay? And by multiplying two square roots together, you avoid having a radical altogether. In this case, if we multiply the square root of 12 by the square root of 12 on both the top and the bottom, what you notice is that the square root on the bottom will cancel out, okay? Here's how it's going to work. You're going to have 2 times the square root of 12 times the square root of 12. Okay? Actually, better yet, this one's actually really easy. Okay? If you notice, okay, you don't even need to multiply by anything. If you notice, you have square root of 12 on the bottom and the square root of 12 on the top. Square root of 12 is exactly the same thing regardless of where it is. Okay, so you can go back and cancel out the square root of 12 because it's the same thing. You have 2 over 12, which when simplified is 1 over 6 because 2 and 12 are divisible both by 2. So that one's pretty easy. Now the second one is a little bit different because we don't have the same square root. Now we could do a couple of things. We can simplify the square root and see if we get this same square root, and that's what I'm going to try to do. So on the top, we cannot simplify the square root because 3 is a prime number. 11 is going to stay outside, but 12 we're going to try to simplify. Like before, 1, 2 is gone, the second one gets out. The 3 doesn't have a pair to go out, so it has to stay inside the bracket. Okay, so you're going to get 2 square root of 3. 2 on the outside, 3 on the inside. Okay, notice now what happens. We have, okay, we have the same square root on both the top and the bottom, which means that they cancel each other out. Okay? And then we would have 4 over 22, both of which are divisible by 2, so you would get 2 over 11 as your final answer. Now we're going to do letter C. Now if you notice, letter C has a cube root on the bottom as well. Okay? So what we need to do in this case is to match the cube root by multiplying both the top and bottom by a number that we know is going to cancel out the cube root. The idea behind canceling out the cube root, okay, is to remember that for the number on the index tells you how many numbers inside the index you need, in the power you need in order to cancel them out. So in this case, since the index is 3, we need 3 square root of 2's in order to cancel it out. So we're going to need to multiply both the top and the bottom by 3 square root of 3 twice. Okay? What does it mean for us? That means that on the top, you're going to have 4 square root of 3 times the cube root. Now, since this will have the same index, we can multiply the inside together of 9. On the bottom, we're going to have 11, the cube root of 27. Now, the cube root of 27 is a perfect cube, which means that this one simplifies to 4 square root of 3 times 3 square root of 9 over 11 times 3, which in turn becomes 4 square root of 3 times square root of 9 over 33. Now, what we need to do next is do both the multiplication and the division. Okay, so remember that in multiplication and division of fractions, you multiply top to top, bottom to bottom. So this is going to become 24 times the square root of 36. Now, you know that the square root of 36 is a perfect cube, a perfect square, so you're going to simplify it into 144 over 10 square root of 3. Now we still technically have a radical in the denominator, okay? So we need to get rid of it. So we're going to have 144 over 10 square root of 3. And in order to get rid of the radical, we need to have a total of 3 radicals with an index of 3. So we have to multiply by the cube root of 3 and the cube root of 3. That way, when we multiply the insides, we're going to have 3 times 3 times 3, which is 3 cubed. Okay? Now, let's recombine them. You're going to have 144, the cube root of 9, over 10, the cube root of 3 cubed, or 27. Whichever one you want to do is perfectly fine. But you'll notice that these two cancel out. So you're going to end up with 144 cube root of 9 over 30, because you now can multiply the 10 and the 30 together. Now 144 and 30 are technically divisible both by 3, and you're going to get, actually both of them are divisible by 6, which is even better. 24 cube root of 9 over 5.